Okay, so today we will start a new chapter, and this chapter is related to the previous one. So we will see that we will do a revision of what we did previously, plus we will introduce a new idea. Okay, so in this chapter we will talk about LU factorization, and it's an operation to solve for a linear system of equation, and we will see in which case it will be efficient. First, before starting with the chapter, we need to do some revision on matrix multiplication. So we should know the following rules about matrix multiplication. First, a matrix multiplication does not commute. So A times B is different than B times A. And the product of two matrices, C equals A times B, is possible only if the number of columns of A is equal to the number of rows of B. So this is the condition to multiply two matrices, is to know that the number of columns of A should be equal to the number of rows of B. And this means that in case A has a size m times n, when we put that the size of A is m times n, this means that A includes m columns and m rows and n columns. Okay, so this will represent the number of columns. Then the size of B should be of the following form: n times P. So here n is represents the number of rows. So this is the condition to be able to multiply two matrices, is that the number of columns of the first is equal to the number of rows of the second. Let us consider this example. So for example, if we give these two matrices A and B, then it's not possible to do their product, because how we do the product? The idea is that when we have A times B, we do the following: A1 1 times B1 1 plus A1 2 times B2 1 plus A1 3 times, we should have an element here. This is why we say the condition to multiply matrices is that we should have the number of columns here. So if we have here 1, 2, 3 columns, we should have 1, 2, 3 lines here. Okay? Okay. So now, if we want to use to multiply A by another matrix, the condition is that matrix D should be with 3 rows, and it can be with any number of columns. Okay, so we can, for example, this matrix A can be multiplied by D1 with 1 column, by D2 with 2 columns, or by D3 with 3 columns. What is common between these three matrices is that the three have 3 rows, and this is the criterion. So if A has 3 columns, we should multiply it by a matrix having 3 rows. So now this is an example to see how the multiplication procedure will take place. So here, if I want to multiply these two matrices, I start by doing the first element. So here, let's say this is C11. Okay, C11 is obtained by doing the following. I consider this is my first line, my first row, this is my first column. So C11 will be the result of the product of these elements of the first row times the first column. So it will be -1 times 2 plus 2 times 9 and plus 0 times 2. So this will constitute now the first element of my matrix C. This is C11. Now C12, okay, C12 will be obtained by considering the multiplication of elements of row 1 with column 2, and C13 will be the result of multiplying the elements of row 1 with column 3, and etc. So this will be repeated. Okay, now when I'm done with the first row. I move to the second one. Okay, so now I will have to take these elements. So this is C21. Okay, C21 will multiply the elements of row 2 with the elements of column 1. So it's 3 times 2 plus 6 times 9 plus 5 times 2. And as you can see, you can deduce that when I do A times B, so this is A and this is B, okay? The result C will have the same number of rows of A and the same number of columns of B, okay? So C will be characterized by same number of rows of A and same number of columns of B. Okay. Now we can practice here with matrix multiplication. So here, for example, if you want to calculate the first rule is satisfied. We have that the number here, the condition, as we said, is to have that the number of columns of the first matrix is equal to the number of rows of the second. Okay, so here this is satisfied, so we can do the multiplication. We start, the first element here is 2 times 2 plus 0 times 9 plus 3 times 2 minus 2 times 7. The second this second element is, so let us take any other if you want. If we take this one, okay, this element, how to obtain it? This is, the number is, so this is C2 3. Okay, so it's obtained by considering the product of elements of row 2 with column 3. So here, if we can verify this, we have 9 times 3, so it's 27, plus 0, plus 0, and plus 5 times minus 3 minus 15, which will give us 12. Okay, so any element we can verify how to find it. Here, for example, this one, this is the result. This is C 3 4. So it's the result of multiplying the third row with the fourth column. So we have 2 times minus 2 plus 2 times 5, and we have here minus 1 times 0 0 and 0 times 9 0. So it's minus 4 plus 10, it's 6. Okay, so try to verify that you are familiar with the procedure by doing this example here. Okay. Now, another important properties in matrix is how to find the transpose of a matrix. So in general, we define the transpose of a matrix as the matrix which we, if you want, we transformed rows into columns. Okay, so we can say that any element Cij in matrix C will become Cgi in matrix in the transpose of C. Okay, so for example here you have and you can see it in other ways, that the row will become a column. So row minus 2 0 is now column minus 1 2 0. The row 3 6 5 is now second row is now second column 3 6 5. And you can verify then that any element, so this element here was C1 2. Okay, in the new matrix it will become C21, and we can verify this. It's here. It's now, it was in the first row, second column. Now in the transpose, it is in the second row, first column. Okay. And in general, we can put it in a general way. So if C is given by C11, C12, C13, C21, C22, C23, C31, C32, C33, then the transpose matrix will be obtained as follows. So the row now will become a column C11, C12, C13, C21, C22, C23, and C31, C32, C33. بتفيد شرب هيدا بالاوبريشن بعدين يعني انا I am introducing these issues because we will use them in this chapter يعني just you should know the definition وحنشوف كيف حنستفيد منها بالcalculation after. Okay. Now, after doing this small review on how to proceed, how to operate matrices, now we will move to the chapter objectives. In this chapter, we will learn how to decompose a matrix into the product of an upper and a lower triangular matrix. And we will learn how to solve a linear system using LU factorization with pivoting. And we will appreciate the efficiency of this method when solving for multiple right-hand side vectors. And finally, we will understand that for a certain type of matrices, computational savings could be achieved by using, for example, the Cholesky factorization. Okay. So now we will start to introduce this new chapter. If you remember, in last chapter, we have seen that when we have a lot of unknowns and we have a large system, high number of equations with high number of unknowns, then it will be very difficult to use Kramer's rules. This is why we come up with a Gauss elimination technique. Okay, but also if you consider, for example, this example here, which was given in the previous chapter, what if I keep the same system of masses and same system of springs, but I just change the forcing? And I'm trying variable possibilities of forces applied to the system. So then, if I want to do Gauss elimination each time I update the forces, it will be also a high time computation. Okay, it will take a lot of time. So this is why in this chapter, in case we keep the coefficient as they are, just we are varying the right hand side, the right hand side vector. This means which is the external vector on the system. So if you remember when we talked about springs and masses, it was the forces. When we talked about the electrical circuit, it was the voltage. So if you keep the same system, just you vary the what you impose on it, then instead of doing each time Gauss elimination, we will develop a method that will allow us to reduce the computational time. Why? Because what will change is only the right-hand side vector, but the matrix A, which we will perform for it forward elimination, okay, will not change. This is why, by taking this into consideration, we can come up with a technique that will allow us to find the solution in a more efficient way. And you will understand this at the end of this chapter. So this is the case we will consider in this chapter. We have k times x. So k is kept unchanged. We are not changing the properties of the system. We are just testing different conditions that we impose on it. So instead of doing each time Gauss elimination to solve, because you know in Gauss elimination, if you remember, the right hand side was also involved in forward elimination. And when you perform an elimination, the right hand side vector is varying. So in this case, if each time B will vary, you should do again the elimination procedure. Okay, to avoid this, we will, in this chapter we will do separation of the what we do, the operation done on matrix A, and then we will see how to deal with it and get the solution for a variable vector B. So in summary, LU factorization is best suited to solve a linear system of equations where the matrix remains unchanged while the external forcing is valid. Let us take the small example, okay? If you have the following, you are solving for these three system of equations. If you want to use the forward elimination method, which we introduced in last chapter, okay? Each time you should compute what is, when we do forward elimination, you should update the coefficients of A, and you should update the coefficients of B, okay? And then you solve for x1 and x2. If you look here, what I'm just changing B. So if you perform forward elimination for these three cases, you will see that what is common between them is A. A is not changing. Why it's not changing? Because I am working with same matrix A here. So when I do forward elimination for these three cases, I will obtain same A, but since B is varying, I will obtain different B's here. Okay, but since I'm using the conventional forward elimination, even if just B change, I should do again the forward elimination. Okay, to avoid this, to avoid every time performing the forward elimination, we will come up with a technique that will separate the operation done on A from the operation done on B. Okay, and this is called LU factorization. This is the LU factorization technique. So now, how will this technique work? We will introduce its concept together now. So let us consider the following example. Okay, we have already considered similar examples in the previous chapter. Maybe it's the same matrix. It's the same matrix because we already applied forward elimination on it. Okay, so let us consider we have this matrix. So if you remember, the first step was to change the form of this system to matrix form. Okay, so now matrix A will be constituted by coefficients multiplying x. So the first column will be formed by the coefficients multiplying x1, which is 6, minus 1, 0, 1. The column here is the one multiplying x2, so 0, 8, 1, 2. Now for the third one, for the third column, it's 2, 2, 6, 2. And for the last one, it's 3, minus 3, 4, 6. Now, this is my form and this is my vector B. Okay, if you remember, in forward elimination, we wrote one augmented matrix. When we talk about augmented matrix, we put A, all terms of A, and then we put, for example, here 6, 0, 2, 3, and we put 1 here. Okay, this is called augmented matrix, which includes the coefficient of A and the coefficient of B, and forward elimination will update all coefficients. This is what will not be done here. We will not consider the augmented matrix. We will not work with these two together. We will do separation of the work performed on A and then the work performed on B. Why? Because what is common, in case we vary only this vector, in this way we don't have to repeat the operation performed on A. This is the whole idea from LU factorization. Okay? So now, what is the idea? The idea is the following. That any matrix, okay, A, can be written as the product of a lower matrix times times an upper triangular matrix. Okay, how to perform this? We have now introduced how to calculate L times U. Okay, you can verify that matrix A can be written as the product of LU in a way that U is the matrix obtained from forward elimination of A. If you perform forward elimination for A, this is what we did in the previous chapter. The previous chapter is very important because it will be used in this chapter and in the coming chapter. Okay? So until now, all we did is the same procedure we have done in last chapter. In last chapter, we learned how we can do the forward elimination to convert a matrix from a full matrix form to an upper triangular form. Okay, so if you remember, together we did this matrix. We transform it into in upper triangular form. So you can go back to the example, and then you can find what will be matrix U. A11, A12, A13, A14, A prime 22, A prime 23, A prime 24, A second 33, A second R4, and A third 4. Now, what will be matrix L? We can prove, and it's very simple to prove, that when you perform forward elimination, you will calculate factors. If you remember, first you do F21 is the factor used for forward elimination of this term, of term A21. Okay, so this was A21. When performing forward elimination, we replace it by 0. Now, F31 is the factor used for forward elimination of this term, and F41 is used for forward elimination of that term. Okay? F32 is for forward elimination of this term, and F42 for forward elimination of this one, and F43 for forward elimination of A4. So when you perform your forward elimination, you will be calculating these factors. And once you are done with the forward elimination procedure, you can verify that if I put the forward factors, the forward elimination factors in a matrix here, and I complete my matrix with ones on diagonal and zeros in the upper part, if I do L times U, I will get A. You can verify this together, okay? You can easily verify this from the definition of your factors. What is F21? F21 is A21 over A11. Okay, and F31 is A31 over A11. And you know that all of these coefficients here, A prime, A second, are related to A's and F. So if you just do substitution and do the multiplication of L times U, you will verify that you will get A. Okay? So now, once we do the forward elimination, automatically we can find two matrices, one lower matrix, one upper triangular matrix, in a way to that L times U is equal to A. Of course, L and U, you have, if you want to decompose A into L times U, you have several possibilities. But one of these that you can easily find, since you know how to proceed with the forward elimination, is this form. Okay, so once you do the forward elimination, you put the upper triangular matrix, and you can create another matrix formed by the factors you used in the forward elimination. So you put them in this form, and then you complete your matrix with one on diagonal and zeros on the upper part, and you can verify then that when you do L times U, you will get it. Okay, now why we are doing this, we will see in the coming slides. Yes, شربل, you start بيو مش لا ما بتبلش باليو, هي L times U, لأنه if you try it, it should be L times U to give you A. Okay, يعني أنت بتجيب اليو من forward elimination أول شيء. Then once you are done with forward elimination, صرت تعرف what are your factors, you can form the L matrix, and you can say then إنه A can be written as L times U. Okay. ايه اكيد بنبلش نجيب اليو بالاول, ما اصلا تجيب اليو بتعوز الفاكتورز, يعني once خلصت من اليو صرت تعرف all factors, you can put your matrix system. فيك تعملهم يعني you can do them in parallel, يعني كل ما تجيب factor بتحطه محله. Okay, and you will get then what is your L matrix. Okay, now we will see why we are doing this, how this can be helpful to solve systems. We will see. So if we go back to the example we have solved together last time, okay, when we performed forward elimination, factor F21 was -1/6, factor F31 was 0, factor F41 was 1/6. So now you can start with filling L. Okay, So when you want to fill L, first you put you have zeros on the upper level, you have one at diagonals, and then you can start to replace factors f as you proceed with forward elimination. Okay, so to start with, we have calculated f21 is minus 1 over 6, f31 is 0, and f41 is 1 over 6. So you can just now replace them here. So this is minus 1 over 6, this is 0, and this is 1 over 6. Now, to complete these ones, I want to know what were the factors I used for in the second step of forward elimination. So also going back to the example we have seen together yesterday, okay, you have, look, if you remember yesterday, we did pivoting, okay, هون بعد ما عم يعملوا pivoting because here يعني هنا they started from this matrix. I considered that we will start from this matrix. Okay. بعد ما عملنا ولا pivoting operation. أول مرة أخذنا this equation as, if we take this equation as pivot equation, okay, هيكون الفاكتور F21 minus 1 over 6, F31 0, و F41 1 over 6. هلا بتاني ستيب 8 اصلا is the highest element، يعني اصلا ما بنعوز نعمل pivoting لانه A is larger than 1 and 2. So we can say that F32 is 1 over 8 and F42 is 2 over 8. Okay, and then the last step is to take this third row to eliminate this term. So هون ما اضطرينا نعمل pivoting. يمكن I don't know if this is the same example بس هول الفاكتورز كانوا هن ذاتهم. Maybe it's another example من اللي عملناه yesterday. Okay, هلا we will do it in details in case it's different. Okay, so here now when you want to assess what is F43 يعني هون ما عدنا نعمل any pivoting لأنه already كانوا pivot element هن أعلى شيء higher than element below them. So F43 is 2 over 6. Okay, so now you can complete L matrix. Okay, and now you can proceed to compute all elements of U. Okay, يمكن it's a different example, so let us do it in detail. إن بس كانوا common يمكن ال factors أول شيء. This is why I thought it's the same example. Okay, so if we want to perform a forward elimination here. Okay, so first, as we said, we start with the following pivot equation. We verify that the pivot element 6 is the highest between the remaining elements, which is the case. And an absolute value أكيد 6 is the highest one. So this is my pivot element, and my factors will be as follow. F21 is minus 1 over 6. F31 is 0, and F41 is 1 over 6. Okay, so now I completed my first column of L. Okay, and I want to complete now. I want to find the resulting transformation in U. Okay, so now what will be my U matrix? This is fixed. This is a pivot equation. It will remain, the coefficients will remain as they are. Now I will start by updating the coefficients of the second row. Okay, how to find the coefficients of the second row? I use my factor. I use my first factor اللي هو F21. Okay, F21 is minus 1 over 6. So I can say that now when I perform the forward elimination, this term minus 1 will become 0. I can verify this. How I can verify this? You have that this element should be equal to the old value, which is minus 1, minus the factor. The factor is minus 1 over 6, times the element above it in the pivot equation in the same column, which is 6. So times 6. I can verify that it's minus 1 plus 1, it's 0. So I verified that this element should be 0. Now, to see this element will not be affected. It will remain as it is. Why? Because the element above it in the pivot equation is 0. So when you have the element in pivot equation 0, then you can automatically say this element will remain as it is. And even if you verify by calculation, you are multiplying a, you are doing 8 minus f, the factor, times 0. So it will remain equal to 8. So this term will not change. Now, concerning this term, for this term, what will happen is that you have, it will become equal to 2 minus your factor f21, which is minus 1 over 6, times the element in the pivot equation in the same column, which is 2. So times 2. This is equal to 2 plus 1 over 3, which is equal to 7 over 3. And now, finally, for minus 3, I will replace it by minus 3 minus the factor f21, which is minus 1 over 6, times the element in the pivot equation in the same column of minus 3, which is 3. So which will give me minus 3 plus 1 over 2, which is minus 5 over 2. And I am done. Okay, with the first step of forward elimination, I am done. Now I will move to forward elimination of the second. Here, what is nice here is that it is already 0. When it's already 0, it will reduce a lot of computation. Since it's 0, then f31 is 0, and all these elements will remain as they are. So here I can just put them as they are, 0, 1, 6, 4. Now, in the next step, I will go to forward elimination of this term. So I want to use f41. F41 is defined as a41 over a11, which is 1 over 6. It's 1 over 6. Okay? So now, how to determine these elements? Of course, first, when I use the factors, this will be 0. I can verify this. Now, for this one will remain as it is. Why? Because the element, if I look at the pivot element in the same column, okay, in the pivot equation, it's 0. So 2 will remain as it is. Now, concerning 2 and 6, for this one, it will become 2 minus 1 over 6 times the element in the pivot equation in the same column of this number, which is 2. Okay, so minus 1.6 times 2, I get 5 over 3. And finally, for this element will become 6 minus the factor, which is 1 over 6, times the element in the pivot equation in the same column of 6, which is 3. So I get 11 over 2.